Now in this problem, we're going to introduce a bit of 2901 to your 2902. And what's happening is that essentially we have a timeline, and then usually in the past, if we go from year to year, we have this fixed interest rate every year. So we just keep multiplying it by 1 plus I, and then eventually you get to time t. But now if I want to tell, but now we're assuming that the interest rate is a random variable. So I1, I2, instead of this constant every year. And now if I wanted to tell you to find the accumulated value at time t, now it's going to be given by an expression that looks something like this. So st, I'm going to define this symbol to be equal to this product over here. So essentially we're doing the same thing as before. So in the past we just multiplied 1 plus I to get us from time 0 to time 1, another 1 plus I to get us from time 1 to time 2, and then after all that we're just going to get 1 plus I to the power of t. And this is because we know what I is. But now we're assuming the interest rate is a random variable. It's going to change, and we don't know how it's going to change. So the best we can do now is to define this random variable st. That's going to be, and in this case, it's the accumulated value from time 0 to time t. And as you can see, all these are random variables. So this is also a random variable itself. So now that we've defined those symbols, we need to find the mean of the variance of the accumulated value. And then what that means is that essentially we want to find the mean and the variance of st. So let's do just that. So going back to the problem over here, in our case the t here is going to be 15. So t is going to be equal to 15 because there are 15 years. And then it is going to follow a uniform distribution. So now we're gonna find the expected value and variance for s15, and then I for any number, any subscript, uniform distribution from 0.07 to 0.1. So now that we know all this, so first of all let's try to find the expected value of s15. And then before we do all that, I'd just like to solve for this expression first, because this is going to come in handy later on when we try to find this. So let's just set this aside and try to find this first. So we have expected value of 1 plus it. 1 is just a constant, so I can write it out like this. And then it is a random variable, right? And then from your 2901, you should know that this formula, the formula for the mean of a uniform distribution, is just adding the two sides together. And in the end, you just divide this by 2, and then you'll get your answer, and then in this case it's going to be equal to 1.085. So this is your expected value of 1 plus it. And then I'm going to do something else. I'm going to try to find this expression first. So this is going to come in handy when we find the variance. So I'm going to solve this first before I start looking for this directly. So solving for this, we get 1 plus 2it plus it squared. So once again, we pull the constants out. So this, you should be fairly familiar with this thanks to your 2901. And now, once again, we just apply the same formula for the expected value. And the expected value for it squared. So in general, the way I think of finding the squares for it, of course you can integrate this directly, but after a long while of taking stat courses, I think most of you should actually be able to remember that the variance of a uniform distribution is given by this formula. So it's the uniform distribution where the lower bound is a, upper bound is b. So if we want to find the square of the random variable, we just take the variance plus the expected value square, right? Because variance is just the square of random variable minus the expected value of the square of the random variable minus the square of the expected value of the random variable. So in order to find this, we just substitute in the formula for the variance. So square. So the square does not apply to the bottom. So this is the variance, and then in order to get the expected value of the square of the random variable, we just add the square of the expected value. So this formula here, I don't know at this point whether you've memorized this. If you haven't, then you can just calculate this directly with an integral, so it works just fine. But if you've memorized this formula, so it's kind of easier to just directly substitute it here, and then just to add the square of the expected value to get your answer. And then once you plug everything into your calculator, you get 1.1773. So both the results that we've obtained here, it's going to come in handy. So now let's move on to the actual question itself. So we're going to use both of these results that we just got. So the expected value of S15 is just equal to 1 plus I1 multiplied by 1 plus I2 all the way to 1 plus I15. And then because all of these are independent, we can actually break this up. So expected value of 1 plus I1 times expected value of 1 plus I2, so and so on. So what we have here is just expected value of 1 plus IT to the power of 15, right? We have 15 terms that are equal to this. And as we found, 1 plus I expected value of 1 plus IT, t can be anything, just 1.085. So this is just 1.085 to the power of 15. And so this is 3.3997. So this is part of the answer. So the second thing we need to do now is to find the variance of S15. Then as you know, this is equal to the expected value of the square of the random variable minus the expected value of the square of the expected value of the random variable. This sounds confusing in words, but this is what it is. So we're going to do something really similar to what we did before. So S square 15, that's just equal to 1 plus I1 square times 1 plus I2 square all the way to 1 plus I15 square minus the square of expected value of S15. We found the expected value of S15, that's equal to 3.3997. So we just square this. And in order to find this, we just do something very similar to what we just did. We just, because all the i's are independent, so all these, we can separate all these random variables and evaluate them independently. So we have this square expected value of this times the expected value of this, so all the way to I15. And then so this is where this result comes in. So we have a 1.1773. So each one of these terms is 1.1773. So we raise it to the power of 15, and then we minus it by this term over here. So this term here corresponds to this term here corresponds to this. So you see why we've derived these preliminary results earlier back then. And then substitute everything into your calculator, you'll find that this is equal to 0.01105. So this is the answer.